the basic concepts of medical instruments. We are going to be working with electrical devices. Do you remember what are the most important components that you need to work with in a medical instrument? Your job is how would we interact with the biological living system, correct? So the sensors and the microcontrollers are the two things that we're going to spend time on. If we look at this car, a quick representation of a circuit where you will have a power supply or a voltage source, and then you have a switch. The switch is the key that you turn on and off the car, and then you have the resistances, which are actually the lights of the car. In order for this to work, we need to have a closed circuit. The switch needs to be turned on, which means that the current will flow, and then all the electrical components will work together. So what is the definition of electrical current? It is the rate of flow of electrical charges, and the unit of a charge is coulomb, and the unit of a current is ampere. What is ampere in the simplest format? It's a rate of change of flow, correct? Coulombs per second. And we have to flow through a conductor and in a circuit element, which is a resistance. So what kind of circuit elements other than resistors? Capacitor, and a switch is an element. You have inductor. Do you remember the inductors? The one that's looped, right? And then you have the diode. Do you remember the diode? So if I want to, draw them, you will have the resistance, you have the capacitor, right? The inductor, and then what's the diode symbol? Was that triangle? That's your diode, right? And those are the elements. And then you have the power source, which is the batteries and all the other things. So the unit is an ampere. We said coulombs per second. Current is a rate of change, which means it's the rate of change of Q, the charge with respect to time. So if you want to find the current, it's the derivative of the flow of the charge with respect to time. It's rate of change. Any rate of change is a derivative for us. And if you would like to find how many charges or coulombs passed through a circuit, you integrate the current, because the current is the derivative of the charge. To get the charge, integrate the current, you get the charge. The important things for electrical circuit, if we have coulombs or charges passing through, is actually the length of the conductor and the cross-sectional area. So what happens if you have a smaller cross-sectional area? Is it easier or harder for coulombs? It's harder. The larger the cross-sectional area, the easier, which means which one has larger resistance? The smaller cross-sectional area. This is a capacitor, that's an inductor, you have a power source. When we do instrumentation, we don't like to speak about resistances and inductors, because now we've passed this, you've completed this. What you need to be talking about is load. 5 resistances, 10 capacitors, and 20 inductors together, that's a load. And I'm going to call it impedance. So if I can combine these two together in one block, right? I don't want to talk about inductor, each element separately. I will call this impedance. So when we look at instrumentation, we're not going to be looking at resistances and capacitors or the small elements. You're going to be looking at blocks, and you will be using, software to say, well, I want to achieve this objective. It will give you a block with an impedance. It doesn't matter what's in it, as long as it's doing what we want it. And then you can send this design to somewhere else, and they are the people, electrical engineering people, who are going to be building that breadboard for you, the circuits. But we would like to talk about impedances, boxes. We have something called direct current, and direct current is a DC current, which is steady. When you look at battery, it will give you the same amount of current. Alternating current, the current is going up and down sinusoidal, and it changes its direction. Now, I don't remember the name. If you watch the movie when, what's his name? Thomas Edison and Tesla were competing who's going to take the contract to build the power lines for the United States of America. The guy who used alternating current won it, because we save energy with alternating currents rather than having a DC current on our power lines. Way much more saving in energy. The sinusoidal currents are really, really more effective than DC currents when we transmit energy. When a current is constant with time, so you can have this, let's say this is the current and this is time. If it's constant like this, that's a DC. If you have a current that's time and is going like this, that's an alternating current in DC. When the current is positive, it goes in one direction, which is when it's negative, it's going in the other direction. So change its direction. That's how we call it an alternating current. Okay, DC for direct current and AC for alternating current, and that's how we are looking at current. This is a schematic representation. See, if it's 2 amperes here, constantly, DC. If it's changing as a sinusoidal, that's an AC. And when we study signals and systems, we're going to learn more about the analysis of the alternating current and voltages. Here, I just want you to know this. You've seen this. We have triangular waveforms, correct? And we have square waveforms. In the lab, when we meet, you're going to be using the function generator to generate all these signals and look at them at the oscilloscope that we're doing. Cool. It's a summary. So I'm going quickly with this, but I will slow down a bit later on. Now, if you have a current, if I told you that's IAB, that means that the current is moving from A to B. If I told you it's IBA, it's moving from B to A. And that is the notion of how we are going to be, using the symbols with us. Cool. Voltage. What is the definition of voltage? Remember last time we talked about voltage, that it is something that is pushing the electrons from one place to another place. So it's associated with circuit elements, the energy transfer per unit of charge that flow through the element. So it's how much energy we are actually putting to move one charge from one place to another place. So let's say if I have this wire here, right? And I have one of the charges, how much energy do I need to push it from this point to that point? That's the voltage, right? And the unit of voltage is volts. Remember work, joules, when we did force in mechanic force multiplied by distance, that's joule, the work, how much I'm going to be pushing something on distance. Now, I'm pushing something, but I need to be it with respect to coulombs. So joules per coulombs, per charges, is actually voltage, the volts. We good with that? Make sense? Okay, let me just erase this. We don't need that. Cool. So the joules in electronics is the same amount of energy in electrical circuits. 1 joule is 1 watt of power applied for 1 second, or a coulomb of electrical charge raised to the potential of 1 volt. I want you just to know that this is the work done to move one charge or from one place to another place between 2 points. Make sense with this? Yeah, I think that's the most important thing. Now, the notion or the notation of voltages. So if you have positive and negative like this, and remember, the current is the direction of the positive charge, right? We talked about that last time. So if this is a positive charge and it's moving from negative to positive, the energy is supplied by the element, right? Like, let's say this is a solar power cell. It's giving you energy. Now, if the charge is going from positive to negative, energy is absorbed by the element. So in this side, let's say this is a fridge, right? And that's a solar power cell. This is how we look at that with these two. So whenever you are either consuming energy or gaining energy, depending on the direction of the current or the charges that we are doing. Now, you can say VAB, the voltage VAB has a reference polarity that is positive at point A and negative at point B, right? VBA, that's B, that's positive. So if I told you this is VBA and I remove this, you don't see that. And I told this is VBA, you know immediately that this is positive and that's negative, right? Make sense? How we look at that, guys? Okay. You can have an arrow in some textbooks, and you can say that the positive reference is at the head of the arrow. So if this is B and A, what is this? Correct? Because the positive is going to be at the head of the arrow. So it's going to be VPA, the notions for it. Okay, power and energy. Power is, so you remember Ohm's law? So V equals I multiplied by R. V equals I multiplied by R. The voltage equals the resistance multiplied by the current. Correct. Now, power, electrical power, is the voltage multiplied by the current. It's VI. That's power. Now, work, remember, power is a rate of change of work. So the power is the derivative of W. W is the integration of the power, right? So power is the rate of change of work. Work is the integration of power. So that's how we're looking at it. Pretty clear. Cool. Now, when current flows, remember, this is an element. For us, it's going to be impedance. It's a collection of resistances, capacitors, and inductors, whatever the circuit is, that's going to be called impedance. And in instrumentation, the expectation from you guys is not to put resistances and capacitors, but to build blocks, something that makes one, functionality, but it's made of multiple circuit elements. and that's called the impedance. Okay, we said that. Good. Now, you remember we talked about the three laws of electronics: the Ohm's law, Kirchhoff voltage law, and then current law. So, what is the Kirchhoff's current law? The current entering, you remember you talked about this, entering a node is zero, which means the summation of all of them should be equal. Whatever comes in should be the coming out. So the sum of the current entering a node equals to the sum of the current leaving a node. And I want you to try this. I don't have pens, I have Sharpies. Oh, there's one. Okay, so find for me IA in each one of these. Remember, we have it's either the net current entering should be equal to zero, which means you need to be able to put positive and negative, or you look at the who. Yes. So let's do the first one. I have this is a node, right? This is my node. That's the point where all the currents are getting in or out. I always use the simplest one. I will say everything comes in should equal to coming out. You need to put a notation, right? Positive or negative, if you want to do this. So what I will say that coming in is positive, or coming in is negative and getting out is positive. So the summation of all these currents should equal to zero, right? So if coming in is, so n is positive and that's negative, coming out, correct? Make sense? So I will say that 1 plus 3 minus IA should equal to 0. So IA, it's negative, right? You move it to the other side so that it's become positive. IA equals 4 amperes. But you need to build the notation. You need to make sure that you are following the same rule. Yeah, so for B, here's what you have. You need to make sure that every wire needs a current to flow in it. So you have 1 and 3, you need to find, and both of them are coming in, right? We need to have a current going out from here. So I will call this IA, right? So you find IA first, and then you get IB with the other ones. In circuit analysis, it has to, because you have two currents coming in this node. What's going to happen with the charges? They need to get out. Make sense? Guys, same thing goes for C, right? You have two currents getting into this point, but what's going to happen that you need to have something coming out. I will call this let's say IA. And then you find on the other node. And do not forget the unit, amperes. And guys, here's one more thing before we move on. See on my first example, I told you it's 4 amperes, but and the arrow is saying it's going out. If I want to really use my notation, it should be negative 4. But as long as I don't want to put negative, say that's coming out, that's like this. Because it should be coming out of that. Okay, let me change the color and let's do we have how much is IB? How much? 2N. So that's 2AN. So let's see. If I have these, this is 1 and 3, both of them are coming in, right? So that's 4. So that should also be 4, correct? Right? Because whatever comes in should get out. So that's 4. Now I have 4 coming in, IB coming in, and 2 coming out. So what I will do, I will say this positive, positive, and that's negative, correct? So we will say that 4 plus IB minus 2 should equals to 0. Make sense? How is this? So what will happen? The 4 minus 2, that's 2 plus IB equals to 0. Move this to the other side, be negative. So IB equals minus 2. So minus needs to be out. So this should be the other direction, 2, right? Yes, not in. It's 2 amps out. Yeah, guys, this is very important. The sign is very important. We good? Okay. What about the third one? Let's erase this. Okay. So for this one here, I have, okay. So we have 4 coming in, 3 coming in. So this should be 7 coming out, correct? Make sense? So this should be correct. So what I will say that's positive, and that's positive. That's impossible. Something should need to get out. So let's follow this notion. So I will say 1 plus IC plus 7 should equal to 0. Make sense? So 1 plus 7, that's 8. So IC plus 8 equals to 0. Move the 8 to the other side, it will be negative. So IC should be 8. Now, sorry, minus 8. So this should be coming out, correct? Because we said positive is going in. So that should be 8 amperes out. So you can say -8, or you say 8 amperes, 8 amps out, in order for the circuit to be balanced. And that's Kirchhoff's. It's a quick review with this. Now, in circuit analysis, I don't know what you did in electronics, but usually you will have a bigger circuit and complete, and then you need to do all of the other ones. Any questions? We good? Comfortable with that? Alrighty. Now, for the other Kirchhoff's law, which is voltage law, the algebraic sum of the voltages equals 0 for any closed path loop or loop in an electric circuit, right? And remember, we don't care about what the inside the box is. It should be a collection of other circuits. But I will, if you have VA that is positive and negative, the direction of where you going from this point to that point, that's negative. From this point to that point, that's positive. And we're going to solve a problem here. So let's say you have this circuit, correct? If I asked you to, how many loops do we have? 3. Now, in order to have a circuit functioning well, you need to have the summation of voltages equals to 0 in all 3 loops. You can't miss any one of them. So can you give me the Kirchhoff's equation for loop 1? So it says we need to move this way, correct? So I will say minus VA plus, see the minus is here, right? So I'm moving from this point. I'm starting from the minus. And then I come here, and that's positive VB. So that's positive VB. And then I have also VC is positive, correct? Plus VC should equals to 0. That's the first loop. Now, here's the thing. You need to have all loops. You have to have equations for all loops. You can't leave any loop. Now, for loop 2, what is the equation? Minus VC, correct? Minus VD plus VE equals to 0, correct? Right? Now, the bigger one, you can go this way, the other way, or that way. I want to change it, but you can do it either ways. So what is the last one? I will start from this point. Minus VE plus VD minus VB plus VA should equals to 0, right? Correct? Now, here's the trick. All of these voltages need to satisfy the 3 conditions for the circuit to be functioning. You can't have any value that does not satisfy the 3 occasions. So you can't have, let's say, VA, let's say 5. If VA is 5, substitute it here, it works. Put it here, it doesn't work. That's not going to work. The circuit will not work at all. And that's one of the things in electronics and instrumentation. Devices sometimes they don't work, not because there's something wrong with the power, or there's something wrong in building the circuit itself, and the instrument will stop working because they don't satisfy the Kirchhoff's voltage law. Does that make sense? And I'm going to show you an example. So let me. Any questions about the loops? Any circuit, you need to build all the loops. You need to find out all the equations for the loops. Now let me give you these. Okay, so let me show you something. See this first circuit here? We have how many loops in the first? How many loops do you think we have in the first one? 3. Same thing, right? So you can do, if we did the notions. I like to work with counterclockwise because that's the easiest thing in science. So this is 1, that's 2, and that's 3. We good? Okay, find V for me. First one. Make sure that you follow the positive and negative signs on them. It should satisfy, each value you find should satisfy all the loops. Yes, it is not possible. It's impossible. And that's one of the things that we find in instrumentations, that someone will build something, put voltages on it, and then the instrument doesn't work. There's nothing wrong except that it's a fault in the design. Let's go with loop 1. Let me find the equation of loop 1. I will start from this point. So plus 3, right? Plus 1 minus V equals to 0. Do we agree? Loop 1. Now, from this equation, what is V? 4 volts. Go to loop 2. In loop 2, what do I have? Plus V plus 7 should equal to 0, correct? Is there anything else? No. So V here equals minus 7 volts. That's a no-no. No, we can't have that. Which means that nothing is going to flow in the circuit. No current, no volt, no nothing. That's also a fault. You can't. So go to the bigger one. So go to the third loop. You have plus 3 plus 1, that's 4. Plus 7 should equal to, how is 11 equals to 0? And that's the problem with a lot of instruments. Actually, when people design, they'll think, well, we have a great idea, let's build it. And when we put it, connected to power, nothing happens. There's something wrong in the design. Let's take 5 minutes and see if you can find V2 and V1 and V3. So how many loops do you have? 1, 2, 3. You can have 4 loops, but let's see if you can get the voltages. So this is called over-deterministic system. We're going to talk about those later on, but you can find the voltages, the 3 voltages. So V1 should be minus 5 volt, V2 minus 7, and V3 equals 3 volt. Just confirm that is correct, and build your Kirchhoff's voltage equations. If you start with this one here, the smallest one, which is the easiest one, so minus V3 plus 3 equals to 0. So V3 is equal to 3, right? Correct? So let's, if I said this is 1, so minus V3 plus 3 equals to 0. So V3 equals to 0. 3 volts. You move it to the other side, change the sign, and then you have 3 volts. Now you can come here also the same thing. Do this as loop 2. So I can go plus V2 plus 7 volts equals to 0, right? So V2 move this 7 to the other side. You change its sign, so that's minus 7 volts. Now here for those V3, so I substitute V2 here to be minus 7, right? And here's the tricky part. You need to make sure that you put minus 7 right here. So put minus 7 as is, right? So how would I formulate this? If I did that as loop 3, I will start from this point. So minus 3. We good here? Minus 3 plus V1 plus 1. Are we good? Now minus 7, correct? So you put the minus and you put minus 7 inside it. Should equals to 0. So that's 7 minus 3, that's 4. So V1 equals 4. Is that correct? Oh, that's 5.
You have to move the V1
So minus 3 plus V1 plus 1
That's
minus
5, and then you have to move it over.
So if I'm doing this minus 7. Oh yeah, sorry. Yeah, so that's 5. I forgot the 1. So positive 7, that's 8, minus 3, that's 5 volts. Correct? To move it to the other side. You good? Are we good, guys, with this? It confused me for a bit. It's what the Yes, so we should be good then. So I just wanted to review the Kirchhoff's laws with you, just to make sure that we are on the same page when we do that. Alrighty, let's go back. Red. Any questions so far? Now, these are the resistors, right? We're going to use a lot of them in the lab, and I don't want from you to memorize the color coding of them, but that's probably something you've covered somewhere else before. But if you want us to go review this, we'll do this in the lab. We can come to the code. That's the symbol of a resistance, and different types of them. We'll come back to those later on. Now, Ohm's law, V equals the I multiplied by R, right? And so it's good to write it this way, but in order to actually analyze the circuit, you need to put the polarities. So VAB equals IAB multiplied by R. So the voltage from positive to negative is where the current is actually passing through it, and that's how we get that. Now, in biomedical instruments, we don't like to work with resistances. Most of the time, we work with conductances, which is 1 over R. It will simplify the analysis for us later on, and I will show you examples why that's important. So instead of having, so we'd like to look at the current. So V equals I multiplied by R. Is that correct? We good? If I want to find I, what is I? It's V divided by R, correct? Which is 1 divided by R multiplied by V. So I can replace 1 divided by R by the conductance, which is the reciprocal of the resistance. So this could be G multiplied by V. So you can say V equals I multiplied by R, and also you can say I equals G multiplied by V. We don't like to divide. We'd like to do multiplication. This is easier. So V equals I multiplied by R, and I equals G multiplied by V. Those are things that we would like to look at. Now, one more electrical component issue is that if I have a wire, just any wire, right? I can find the resistance of that wire if I know the cross-sectional area and the length, and something called rho, which is the resistivity of the material. So different materials will have different resistivities, and that will result in different resistances. So if a wire is made from silver as opposed to copper, the silver and copper have different rows. So this is called the resistivity, right? Yeah, and it changed from one material to another materials. So different materials have different resistivities, and that's how we select. That's why you can find, let's say, an instrument that is very expensive is because the material that the wires are made of are actually different and much more expensive. In your iPhone, there is a substantial amount of gold actually in the iPhones. That's why companies want to buy back your iPhone from you, and they're making a lot of money actually. So don't feel that they are doing you a favor. They're actually getting a lot of gold out of these instruments. Okay, so the cross-sectional area is A. So rho multiplied by the length divided by A is actually your resistance. That's how you calculate the resistance. If you have a wire with a length and you want to find that thing. We good? Alrighty. Now we would like to start with medical instrumentation. So that was a quick introduction just to get ourselves familiar with what we want to do. Now, the components of a generalized medical instrument system. Again, what are the things that we need to focus on? The sensors and the microcontrollers, right? This is it. Everything else is electrical engineering. We can find someone else to work that for us. But your job as a biomedical engineer is to work with the sensor and the microcontroller. Now, the components of it, let's say I went to the hospital and I want to look at the MRI device, the magnetic resonance imaging device. What are the components of that device? That's an instrument. You can think of an ECG system, whatever, anything in the hospital. They have to have these specific components. Component one, we need a data acquisition system. This is the hardware and software that generates and store data for instrument. Remember when we did the experiment with the iWorks, the EMG, that we collected with the dumbbells, right? So that is a data acquisition system, and that is our job, to work, to design, and to calibrate, and to do preventive maintenance. So if someone hires you in a hospital, they will expect from you, we don't want to do maintenance for the device, the electrical components, but we would like to make sure that you as a biomedical engineer know how it works and know how to operate it, and then do calibration and preventive maintenance. Okay, signal processing unit. What is that? And it is the Arduino and the Raspberry Pi, right? So the first two of them are the most important for us as biomedical engineers. So this is the system that processes the data from the instrument and converts it into useful information. Now, if you go today, if we went to the hospital and we break into, we open the MRI device instruments, inside it you will find some form of Arduinos and microcontrollers and Raspberry Pis. It's not the same, but it's a custom made one for that MRI, but it has the same functionality and you can program it the same way. Does that make sense? So whatever we're going to learn here using Arduinos is the same thing in those big fancy equipments. And you can see that they multiply their prices by 10 folds. Anything medical, you multiply by 10. So the cost to build it is low, but because it's medical, they're just charging people a lot. And because they have to do regulations and other stuff. Okay, data acquisition, we got, those are the sensors. Signal processing unit, that's the Arduinos, the microcontrollers. Those are the two things that we're going to be focusing on. Then you will have the control unit, and that's also the control and the signal processing unit. These two are both in the Arduino, because the Arduino is going to make decisions, right? It's going to tell you that, turn on one light, turn off that light, start acquisition, stop acquisition. So these two are actually the same. For us, it's the same components. The signal processing and the controller is the same, which is the Arduino, the one that I showed you last time. Control, the instrument allows for manual or automated operations. Then you have the display unit, screens, right, and display unit. And actually, this is an accessory. So these accessories are what medical instrument companies make money in, actually, because of these accessories. But for us, we can have a small LCD. You remember the one that I showed you last time? That's enough for us. But if you want to make it fancy, and that's where they make money. And then you will have the power supply. We're not going to go into power supplies. That's electrical engineering. So if you're studying electrical engineering, that's your job, to design the power supply for them. And then you have the communication network. That's also electrical engineering. If you want to do the transmission of data, but we're going to use Wi-Fi. There's a Wi-Fi module for Arduino. So if you go online, you can search that Arduino modules. There is a Wi-Fi module and there's a radio frequency module for communication. And there are antennas that you can add. We're not going to design them. We're going to use them. And I'm going to show you how to program those. Does that make sense with the communication? And those 6 parts are the things that, make any biomedical instrument. We're going to focus on the first 3. Those are our main focus. We would like to know how to use them and for what purpose. And we're going to learn a lot about their different types and modalities. Does that make sense? And then you should be good. And that's so if you want to imagine a generalized medical instrument, remember the difference between biomedical, electrical, and mechanical is that we need to interact with a biological living system, correct? That's the thing. Our data or signals that we are collecting are different, and the safety considerations are different. So if I would like to imagine a medical instrument, this is it. This is what we find in hospitals. You have a patient. We need to measure something. We're going to call it a measurement, right? So you need to measure, let's say, temperature, or you need to measure blood pressure or heart rate. You want to measure EEG, the brain activity. That's the measurement. What do we need to measure that? You need a sensor. So we need a primary sensing element, right? This is it. See the solid line? That means this is biomedical engineering. We're going to learn everything about these sensors and why we are using these sensors and how to design them, what the advantages, what are the disadvantages. If you work with, let's say, with blood pressure, you need to know all the sensors that are related to blood pressure, who makes them, how much they cost, and how to use them with an Arduino. Whatever they're building in their manufacturing facilities is this. What did you call the thing that converts one form of energy to another form of energy? Transducers. You need to transform, let's say, mechanical vibration into electrical signals. You need to transfer electrical signal of the brain to a simpler electrical signal that we can, which is not simpler, a magnified electrical signal, so that we can see it. So that's transducers. That's solid line, right? Then what do we have? Signal processing. Remember the control, the microcontroller? That's our Arduino. Another solid line. You need to have a screen to look at the data. When you have output, show it to the physician or healthcare providers to make decisions. Everything dashed is actually accessories that we can add to the device to make it work better. So you can have, after you do processing, you can store data or you transmit data. You can either store it or you can send it somewhere else. You need a power supply, or you can have a battery on it, or you can have a solar panel to, a solar power cell to power your device. Or the fanciest one is that you can use the heat temperature of the body to charge a battery. Now we have these types of batteries, especially for pacemakers. It uses your temperature to actually charge and recharge, which is really, really fancy technology to have. And then you have control and feedback. So let's say you are a subject and you're looking at your, data, and let's say, there is something called therapeutic robotics, that you can stand on like a treadmill and you can work and you increase your heart rate and you can lower your heart rate. So that feedback can come to you, and then you can slow down or you can increase your, speed, so that you can do your routine or your physical therapy routine. So the feedback from the screen is important. And then you can do calibration signal. Now, calibration is something that you need to do as an engineer in the hospital. Before anyone can use a medical device, there is a calibration procedure to make sure that the device is actually measuring what it's supposed to measure and it's giving you the right numbers. So if you are hired in a hospital, your job will be preventing maintenance, calibration most of the time. We don't do maintenance. You're not going to fix something in the hospital. We usually outsource this to the company that made that device. We will have maintenance contracts with them. So that's how the model works. Now, this is the measurement. You can affect the measurement with something else. For example, let's say I would like to look at my brain activity, but I'm in a room that changes its color. So that changing is a stimulus signal for the subject to measure all the other things. Does that make sense for us? And that's all what it is actually of a generalized medical instrument system. Now, here's the thing. You can pick and choose which one do you want to specialize in. Do you want to specialize? I like the sensors. I think that's the most valuable thing for biomedical engineers, is to work here, design different sensors. calibrate those sensors, make them smaller, make them automated, use nanotechnology, use 3D printing to build these things. Everything else outside the sensing and the controller, the microcontroller, is something that other people can do. You learned about anatomy and physiology, correct? And you know about cell biology. So you know exactly what's happening in the body. You are most valuable in this here, in this interface. Does that make sense of how we look at that? And that's what I want from you to learn in this class. Do we know all the different types of sensors, and we know how do they work and why they work this way, and then design new ones and have innovation in the sensors and the controller, the signal processing. You will learn MATLAB, correct? But I want you to learn about not just after getting the data. I want you to design something to collect the data, which is using the Arduino and the microcontroller. Make sense? We good? So sensors, I've highlighted them. This is what we want to work on. Signal processing. That's the microcontroller. You can look at the display, but it's just a screen. It doesn't matter. For me, it's nothing, fancy than other ones. We good? Any questions? Yes. Oh, please. Yes. Let me put a Dropbox. We good with this? Right. Now, guys. By the way,